did it go? It went to heat. Okay? Well, in this system, there's no kinetic energy at all to begin with. They're both just standing there. And afterwards, they both have some. Now, if you ask me, doesn't it still add to 0? This is where I remind you, energy is not a vector. So it doesn't matter that one's going to the right and one's going to the left. They both have 0 kinetic energy to start with, and afterwards they both have some. So there's more kinetic energy in the system. Where did it come from? Where does this sudden found energy come from? Chemical energy, that's right. So we have an internal non-conservative force, but now we have that the kinetic energy comes from chemical, and of course it's not easily put back there, okay? So before, the non-conservative work was negative and removed energy, mechanical energy. Now it's positive and it adds energy. So you will find that the kinetic energy of the system now, the kinetic energy of the system initially, finally it's actually more. And that's good because at the beginning it was 0, so you can't have any less than that. You can only have more. And now we have more because they're both moving. So these internal forces can both introduce energy from inside or dissipate energy to the environment from inside. Okay? So these are called inelastic collisions. These things often get called explosions. Now obviously there's no explosion involved here, but there is a release of chemical energy from the people. Another example would be if you just literally had some kind of exploding bomb on ice, what would happen is that the internal force would release chemical energy into kinetic energy. The fragments would fly everywhere, obviously much more kinetic energy. But if you counted up the momentum of all those fragments, some of them would go in this direction, some of them would go in this direction. The momentum of all of them would still add to 0, which is what it was when the bomb was just sitting there. Okay? There's that situation. We have elastic collisions, inelastic collisions, explosions. Let's keep going. Any questions on these before I move forward? Okay, so let's see if we can knock out 2 more. I'm running out of room, so let me go over here. Keep the same column headers. Hopefully you have more room than I do. Here's my next scenario. I have a ball that's falling through the air. And that's my system. That's just one object alone. So is the momentum conserved? Can anyone tell me, is the momentum of a falling ball conserved? Well, momentum is just mass times velocity. So is the velocity the same? No, it increases. So what happens to the momentum? Increases. So is the momentum conserved? Definitely no. It increases here. Momentum is increased because there's an external force, which is what? Gravity is the external force, right? That's fine. Momentum won't stay the same if you have an outside pull, and we have an outside pull here. How about mechanical energy? Is that conserved? KE plus PE? Yeah. Because remember that gravity is conservative. So the force of gravity is conservative, which means that it's just taking energy from potential, putting it into kinetic, but the sum total is constant. And of course, the very reason why we include both of those forms of energy under the umbrella of mechanical is because if we wanted to, we could throw that ball back up and reverse the process, right? So we happen to be sloshing in one direction right now because the ball is falling, but we can get it to recover going the other way. So that's why we would attack this problem with energy conservation, and this is the kind of thing you do on homework number 7, because here energy conservation is the way to go. Momentum conservation, well, momentum's not conserved. Unless we can somehow take this external force that acts on our object of interest and invite whatever's causing it into the system. What is that pull coming from? The Earth. So if we invited the entire Earth then into the system, if this was our system, is the momentum of the Earth plus ball system conserved? Yeah, because now we've taken the thing that was that pesky external force and brought the thing that caused it inside our system. Now it's an internal force. We would have no reason to do that. We can solve this problem usually with energy conservation. But let me point out that if you have a falling object and then it falls and hits the Earth, that's a collision like any collision, right? So we can analyze that with momentum conservation. So you could say, well, the momentum of the ball is not conserved. Not conserved. You can say the momentum of the ball plus the momentum of the Earth is conserved. Because we've taken the force of gravity and we've taken it from being external and we've made it internal. That's sometimes the game you play when you're trying to figure out how to use momentum conservation, is to invite everything that is a significant influence, invite it into your system, where then they will just trade momentum, not change the total. Right? Any questions on that? Okay, let's do one more. This one, I'm going to have a block. It's going to slide along a surface. The surface is going to have friction. And my system is, for the time being, just going to be this block. Okay, so momentum, we're thinking internal versus external. Is there an external force on this block? Yes, there is. So is momentum conserved? Nope. No. Momentum is decreased because of the external force of kinetic friction. Okay? Now if we're looking for mechanical energy, we have to ask what kind of force is friction? Is friction conservative or non-conservative? Non-conservative. So do we expect the mechanical energy to be conserved? Nope, that's going to decrease too. Force of kinetic friction is non-conservative. It takes kinetic energy and it sends it to heat where we can't get it back. So can't do that either. So how would we attack this problem if neither conservation is available? Well, one of the approaches we could do is to try to pull the same trick we pulled in the previous row. Whatever is the cause of the force, let's invite it in. So the cause of the force is this frictiony surface. So let's say it's from a table. Well, then the table is sitting maybe on a frictionless surface, so it's on and on and on, so can't do that. But let's say just for kicks that the table itself was on a ice. I don't know why you want to do that. But that's a way you could suddenly cut off and say, okay, I can isolate the block in the table from the outside world. So now I can have my system be the block plus the table. So while the momentum of the block itself is not conserved, you can, by inviting the cause of that in, you can say the momentum of the block plus the momentum of your table is conserved. Again, we took the force of friction, which used to be external, and we made it internal. There we, of course, got really lucky if that table is sitting on a frictionless ice, okay? Then it just would be an odd way of having a collision, right? What we do is that object A would be the block and object B would be the table. You don't literally ram them into each other like we do with collisions, having the normal force be the thing, right? It'd be an odd way of causing a collision, but it meets the definition of a collision, right? You slide that object onto the top of the table, A would slow down and B would speed up. So what you'd end up having at the end was presumably would be A and B sliding together across the ice. It'd be a way of causing a collision by sliding friction instead of with a head-on or glancing collision, okay? So that would be unlikely, right? You'd be lucky to be able to cordon this thing off and say that there's no friction between the table and the ground. So rather than doing this approach, I would actually say, use the approach you did on your homework number 7. Use energy, because with energy, even if you have non-conservative stuff going on, it's more than happy to work with you on that, okay? You just include the non-conservative work term and go about your solution. So let's catalog, okay? I left this Venn diagram up here on purpose so we can catalog all of our cases. We have case 1, case 2, case 3, case 4, case 5. Let's figure out where they fit in on our Venn diagram. The elastic collision, internal conservative force, so we have, luckily enough, both conservations apply. For cases 2 and 3, momentum was conserved, but because there was a non-conservative nature to that internal force, we either had energy coming in or going out. So over here we had cases 2 and 3, where both examples where momentum was conserved, but the mechanical energy was either increased or decreased, not conserved. Case 4, in its original form, not the weird form that I talked about later where we invited the Earth in, with just the ball, we found that momentum was not conserved because gravity was external, but gravity is conservative. So that was one of these. This was case 4. And then finally, we came up with case 5, which in its original form, neither was conserved. So you're not expecting either quantity to be conserved, but luckily, energy conservation does have that in and out valve built in, non-conservative work, so that you can still get the problem solved. Okay, so if you understand everything that's on the board right now, that is a major achievement in Physics 1, okay? To be able to look at a system and know which conservation, perhaps both, perhaps just one of them, perhaps neither, would be applicable, and knowing how to solve from there what you want to solve. So of course the physics is picking out which thing is conserved, and then the math is just the details. Okay, any questions on that? Okay, so that I think is a good timing here because that completely closes out our momentum unit. There will be some other stuff as well on your homework number 8. So we're still building that stuff up, but this will be heavily featured. Let me get to your exams. So I've already posted a complete grade summary for you on the WebAssign. You'll find it there. But for right now, I want to give you some preliminary statistics. This is Physics 111, 12, 15, Exam 1. The mean score was 62 out of 110. That is 56%. That is about, if you notice, the past 3 cohorts did not dip below 60% at any time. That's not great, okay? And for that reason, I'm not going to, for that, set this to a B+. It will be a high B, okay? I need to see some higher stuff in relation to past cohorts to be able to justify setting the mean at the same point. And the standard D was 22 points. That's a letter grade. So if you're 22 points above the mean, you have an A. If you're 22 below, you have a C, and whatever fraction thereof. On the course webpage, you can see more exactly. The minimum score was, lowest score was 25.5, and the high score was perfect. Okay. All right. So let me call your names out. Come on up and get your exams.